Welcome, students. Today we will solve important sample problems from surface areas and volumes.
Imagine dipping this cube into a bucket of paint. The surface area isn't the total volume of the object. It is only what the paint can touch. Any face hidden on the inside is ignored. We can apply this logic to a medicine capsule. At 14 millimeters long with a 5 millimeter diameter, the shape looks complex, but it is actually just 3 distinct paintable parts, 2 hemispheres and a central cylinder. To find the area, we need the height of the middle cylinder. Since the diameter is 5, each end has a radius of 2.5. Subtracting the ends from the total length leaves a cylinder height of 9 millimeters. Now we just add the curved surfaces together. By calculating the areas of the 2 hemispheres and the cylinder, we reach a total of 70 pi, or about 220 square millimeters. When shapes are joined end to end like this, with no hidden faces between them, the calculation is a straightforward addition of their exposed parts. Things change when shapes overlap. Take a 7 centimeter cube with a hemisphere of the same diameter mounted to the top face. If you simply add the total area of the cube to the area of the hemisphere, you'll get the wrong answer. An X-ray view reveals why. There is a circular boundary trapped inside where the 2 shapes meet. Because that circle is now inside the solid, it can't be painted. We have to subtract that hidden area from our total. Removing that one circular base gives us the correct surface area of 332.5 square centimeters. This is a key principle of composite geometry. Any hidden connection points between shapes must be subtracted to avoid counting surfaces that are no longer exposed. We see the opposite effect with cavities. If we take a solid cylinder and use a laser to carve a cone-shaped hole out of the top, we are removing physical material. Even though the object is smaller, the surface area actually increases. By hollowing out the center, we've created new internal walls that the paint can now reach. To measure this new space, we use the Pythagorean theorem to find the internal slant height. With a radius of 0.7 and a height of 2.4, the internal slope is exactly 2.5 centimeters. To find the final area, we take the cylinder's outside surface, add the new area inside the cone, and then subtract the circular opening at the top where the middle was removed. This gives us a final area of 18 square centimeters. Every cavity adds its internal geometry to the total, while subtracting the flat face used to enter the shape. Imagine a cube with a side length of L and a hemispherical depression carved into the top face. Pause here and try to write out the algebraic formula for this solid surface area based on the logic we've covered. We take the cube's 6 sides, add the curved surface area inside the bowl, and subtract the circular opening on top. Simplified, the formula is L squared over 4 times 24 plus pi. Compare this to the mounted hemisphere from earlier. Even though one is a mountain and the other is a valley, the algebraic result is exactly the same. Textbook math problems usually give you perfect, isolated cylinders, cones, and spheres, but the physical objects we actually build and consume are mathematically messy combinations of these shapes. To find the volume of everyday items, look at this medicine capsule and this ice cream cone. We can visually split them apart into their core geometric primitives. A capsule is simply a cylinder capped with 2 hemispheres. An ice cream cone is a cone with a hemisphere resting inside. Here is our baseline example, a 3D solid formed by a cone perfectly resting on a hemisphere. We know both shapes share a radius of 1 centimeter, and the cone's height is also exactly 1 centimeter. To find the total volume, we simply add their individual volume formulas together. 1/3 pi r squared h for the cone, plus 2/3 pi r cubed for the hemisphere. We plug in the ones, add the fractions, and get exactly 1 pi cubic centimeter. Notice that we didn't calculate the decimal value of pi. Leaving pi as a symbol until the very last step keeps the math perfectly clean. Trying to multiply out 3.14 in the middle of a problem creates messy decimals and opens the door for arithmetic errors. Real-world blueprints rarely hand you every internal measurement on a silver platter. Often, you are given the overall length of a part, and you have to deduce the rest. Take a look at this 3D metallic engineering model. We know the total end to length is 12 centimeters, the overall diameter is 3 centimeters, and the cones on either end each have a height of 2 centimeters. We need to calculate the volume of air inside, but we are missing the height of the central cylinder. Watch the 12 centimeter bracket on top. If we subtract the 2-centimeter cone on the left and the 2-centimeter cone on the right, the bracket shrinks to 8 centimeters. That is the hidden height of our cylinder. With a cylinder height of 8 and a shared radius of 1.5, we calculate the cylindrical section to be 18 pi. For the end caps, calculating both together gives us 3 pi. Again, pi remains untouched. We add 18 pi and 3 pi to get 21 pi. Now, at the very end, we multiply 21 by 22/7 to get a clean final answer of 66 cubic centimeters. You cannot trust top-line measurements at face value. You must structurally analyze the shape and subtract known external parts to deduce the dimensions of the internal components. We can apply this exact same logic to a famous real-world problem. This single gulab jamun is shaped like a cylinder with 2 hemispherical ends. The total length is 5 centimeters. The diameter is 2.8. We need to find the total volume of sugar syrup in 45 of these, knowing the syrup makes up 30% of the volume. Pause the video right here. Use this subtraction logic to find the hidden height of the central cylinder and write out your total volume formula. Since the diameter is 2.8, the radius is 1.4. That means each hemispherical end takes up 1.4 centimeters of the total length. We subtract both of those from 5, leaving a cylinder height of 2.2 centimeters. If we try to calculate each section individually now, the decimals will get overwhelming. Instead, we write out the combined formula. By factoring out the common terms, pi and the radius squared, we consolidate the messy decimal fractions into a single clean parenthesis before we do any heavy multiplication. That gives us the precise volume for a single piece. We multiply that result by 45 to account for the entire batch. Finally, we multiply that batch volume by 0.30 to calculate the 30% syrup concentration. The result is approximately 338 cubic centimeters. Scaling up to dozens of complex items isn't about raw calculating power. It requires setting up your algebraic structure correctly before you begin solving. So far, we've built complex objects by adding primitives together, but manufacturing often involves the exact opposite process, carving material away. Look at this wooden pen stand. It starts as a solid rectangular cuboid, 15 by 10 by 3.5 centimeters. Then, 4 identical conical cavities are drilled into it to hold the pens. Each hole has a radius of 0.5 centimeters and a depth of 1.4 centimeters. The mathematical framework here is subtraction. To find the volume of the remaining wood, we take the initial volume of the cuboid and subtract 4 times the volume of a single conical cavity. Multiplying length, breadth, and height gives us 525 cubic centimeters of solid wood. We calculate the volume of one tiny cone, multiply it by 4, and get roughly 1.47 cubic centimeters of removed material. Subtracting that from the base leaves 523.53 cubic centimeters. As you can see in these 4 models, mastering 3D volume comes down to 3 rules. 1. Deconstruct the object into basic primitives. 2. Find the hidden dimensions by analyzing the total lengths. 3. Determine whether you are adding pieces together or subtracting empty cavities. Whether you are calculating the air inside an engineering manifold, measuring syrup in a bakery, or calculating material costs for a milled piece of wood, these 3 steps allow you to exactly measure the physical objects around you.